I will start stammering then. Hello, my name is Sam Falvo. I am today's makeshift videographer. Unfortunately, I need to use my computer to give the presentation, which is why I'm recording my desktop instead of me. So today I wanted to talk a little bit about a programming language that I haven't actually worked with in a couple of, I want to say more than, we'll just call it more than a year. It's called BSPL.
Which stands for?
It stands for Basic Systems Programming Language. Has no relation to BASIC. It's actually a Forth-inspired programming language. The history of BSPL is, well, while I'm working on the Kestrel 3 project, or even the Kestrel 2 DX, I'm using the RISC-V instruction set for the processor. And I really wanted to use something like Machine Forth to program it, because it's less than 500 lines of code to write a Machine Forth compiler for almost any complex instruction set computer you can imagine. But on a RISC, Machine Forth does not map very well at all to the underlying architecture. If you take the most naive approach, the typical Machine Forth primitive, whether it be stack manipulation or even something as simple as addition, ends up being close to 3 to 4 machine language instructions. Now, if these were compactly encoded instructions, not a big deal. Unfortunately, in most RISC processors, your instructions are 32 bits wide. So you're looking at 12 to 16 bytes of object code corresponding to one Machine Forth primitive. That is rather unacceptable to me, because that would result in programs that are just absolutely ginormous in size. And since the Kestrel 2's address space totals about 48 kilobytes of memory, that would have been absolutely prohibitive in that particular case. The Kestrel 3 has 1 megabyte of memory available to it. Not so big of a deal there. But nonetheless, having small binary sizes is convenient for other reasons as well. So I decided to put that away for a bit, start working on a custom-made assembler. The assembler works nice. It's written in Python. I can use RISC-V mnemonics and so on and so forth. Wrote a lot of good code with that. But then it's like, oh, for the original Kestrel 2, which had a 16-bit stack processor, I wrote an operating system for that called STS. Stands for Single Tasking System. It's kind of a crude hodgepodge of CPM combined with TriCOS. Basically, do the absolute minimum thing that could possibly work sort of deal. And it works insofar as I was able to bring up a shell. Then I quickly ran out of memory again. So I was like, okay, I need more memory space. So at the time, I wanted to build a software emulator for the Kestrel 3, which had more memory accessible to it, at least a megabyte. And so I was like, but I need an operating system for this new machine so that I could start doing software development on it, so, actual hosted development. So I was like, okay, how can I port STS, which is written in this stack assembly language for my 16-bit CPU, and port it to this RISC environment, and yet still be efficient enough that I can run it, reasonably well. And as we saw in our last presentation, having a defined scope is incredibly useful. And BSPL was defined largely by that problem as its establishing scope. So I'm going to kind of walk through what BSPL is currently. I'll show you maybe a little bit of some code example. And then if I still have time, I'll go through and I'll talk about some of the things that I would like to change with BSPL coming up for the Kestrel 3. So this is, it's all in the Kestrel repository, by the way. This is on GitHub. And it's under the source BSPL directory, and the root entry into this is the .fs file, the bspl.fs, because it is written for G4, as you can see here. The way this, I can basically tell you exactly how this works. The mindset was, how can I compile machine forth into a form where primitives more or less, or come as close as possible to matching RISC-V instructions one for one. It's not quite perfect in that regard, but it comes really close. And the way that I came up with this was, well, I was reading a paper on I forget how they described it, but I'll just call them micro passes. Basically, the idea is, instead of having a one-pass compiler or a two-pass compiler, have 20 passes, 40 passes. But the thing is that these passes do exactly one thing, and they do exactly one thing very, very well, right? And so that's the approach that I took here, right? So I've got I got 5 passes here, right? And the first pass is the most obvious one. It basically accepts your machine forth input and produces a stack, an idealized stack notation in a buffer inside this compiler. LGP is the next pass. This is, what this does is it basically addresses an architectural quirk of, which is actually common in most RISC processors, including the ARM, but it's particularly acute with the RISC-V because we only have 12 bits of displacement from a base register to load from. So if I need to add or load a numeric constant that falls outside of the range -2048 to 2047, I have to store that number in memory, and I have to load it relative to the program counter. The problem is, the program counter is not a general purpose register. So I have to load the value of the program counter into a general purpose register first, and then reference off of that. GP is called the global pointer register, and that's the register that I use for that purpose. The name GP, by the way, comes from the C ABI. It's not actually an architecturally defined role for that register. It's just how they use it conventionally. Prologue and epilogue. That is a pass that then says, okay, now that we've got our ideal runtime operating environment set up, how do we handle subroutines? Or,
What was that again?
I said, now that we have our ideal operating environment set up, how do we handle subroutines? Because it turns out that at least the way I write for it, an awful lot of my forth definitions use nothing but primitives. When my code tends to make use of, how can I say this? So the high level definitions, of course, call the next lower level, which call the next lower level, and so on and so forth. Everybody who codes forth knows this. But there comes a point where I have like a screen full of lines of code where it's like, okay, what I'm doing now is loading a constant and loading a constant plus, if this, very low level basic primitive stuff that should be handled by individual CPU instructions. For the way the RISC processors work, I don't want to have to load and store my prologue and epilogue code if I don't make any other subroutine calls. That's just wasted time, it's wasted space, and also a lot less registers that I have to deal with. So what this does is that basically this is a pass that goes through and says, do you make any subroutine calls? And if you do, then and only then do I annotate the code that says, okay, I definitely need a prologue at the beginning, and then it locates every call to exit and then precedes that call with the equivalent epilogue code that's appropriate for that place. At this point, I have code which is more or less semantically equivalent to a RISC-V assembly language listing that I would write by myself. So the next step is to convert it into using, or is to translate stack operations into register operations. So here, basically, what I'm doing is assigning registers to ordinal stack locations. Now, this gets really complicated, not so much in implementation. The actual code is very small. But it's very complicated to actually wrap your head around when programming in. And I'll show you examples of why that is coming forward. And then finally, the asm.fs pass that actually generates the actual assembly language listing itself. At this point, everything exists in RISC-V code. And as you can see here, I am actually generating text output. These are RISC-V mnemonics. So I'm not stuffing bytes into memory and then executing them like you would expect to find in an interactive fork environment. This is actually a static compiler. You feed it source code in, you get an assembly listing out, and then you pass that through an assembler to get your final binary. So in this sense, BSPL has a lot in common with classic C systems, for example. And then in case you were wondering, this is how I drive everything. Basically, I've got the colon definition down here, which invokes pass 1. This is an initialization routine. This resets all my buffers and global variables and such. And then after we do pass 1, we define our symbol, right? So for example, if I say colon pass 1, we pass 1 to extern, which I kind of scrolled by above, but basically that just creates a symbol in the dictionary. After that, we then execute passes, which does exactly what I said. Load global pointer, locate the prologue and epilogues, we translate to registers, and then we generate our assembly. It literally is that simple. So this is what the first pass looks like. This is actually, in terms of lines of code, this is by far one of the largest modules. It is 366 lines. This would basically be your traditional machine forth compiler. But what it does is, instead of encoding it into like tiny little 5-bit opcode slots, every machine forth primitive gets an entire word or a cell of memory, the lower 8 bits of which is the opcode, just for convenient manipulation. And then any parameter that is required gets tacked onto the end there. So you can kind of think of this machine forth environment as being, and I think Phil Koopman would describe this as an SS1 forth environment. I won't go too much into detail here because, as I said, all of this is up on the web, on GitHub. It's reasonably well commented. But one thing to note is because I am targeting a processor that can deal deftly with 8, 16, 32, or 64-bit quantities, I've got a large number of fetches and stores. And then I've got CFetch and CStore and regular fetch and store defined as aliases for common types, which you can redefine if you want, but at least that's the most forth-like. And as you can see, in terms of most of your instructions, very, very simple. You just push a number on the stack and you just dump an instruction in memory. If you do need a parameter of some type, you can always rely on a construction such as this. So the idea here is whatever value is on the stack, you make space for the opcode, be it 8L shift, you put the opcode into the lower byte, and then you record it. So there's no back patching or anything like that. So in some senses, this is actually simpler than your traditional machine forth compiler. Now, I want to talk about these stack manipulations. Basically, this was my answer. One of the big problems with mapping machine forth to, or any forth really, to a assembly level implementation, one that's really efficient. I'm not talking about, like for example, MPE forth or Swift forth. Yeah, they assemble to native machine language, but they kind of cheat a little bit. Like if you look at their disassembly of their colon definitions, for example, they're pretty efficient, but they're not like the most efficient that you can possibly eke out of the compiler. But they run good enough for their needs, and that's fine. For a RISC processor, that type of corner cutting would basically lead to excessively large code. Not necessarily slow, just large. And since each machine language instruction is already 4 bytes in size, I want to make sure that I minimize that to the greatest extent that I can. One of the problems is mapping the data stack to registers in a way that is compatible with both variable output words. So for example, the ANSI forth word find can return either 1 or 2 items. I'm sorry, 2 or 3 stack cells on the stack. And you have no idea what it's going to return until you actually invoke that word. So the subsequent code that uses the results from find, somehow has to deal with that. The other problem is how do you deal with input parameters without having some kind of syntax at the head of the word that basically says, I accept A, B, C, and D as input parameters, right? Somehow the compiler has to know whether or not something's on the stack. Now, at the time, as forth programmers, we're already very familiar with to, our from, our fetch, our store, that sort of thing. But my solution to this particular problem was to make the same set of operators for the data stack. So I have 2D, D from, D fetch, and D store. And D fetch and D store, by the way, are more or less, you can kind of think of them as pick and put, in a sense. But long story short, this is probably the biggest departure from your typical fork. And the answer as to why is because I treat the registers as a separate evaluation stack. So this is really describing a 3-stack machine. You have your return stack, you have the data stack that you actually pass parameters on when you call words, as well as return results on, and then you have your evaluation stack. The evaluation stack is local to a word. Actually, scratch that. It's local to a basic block. So unlike most programming languages, you have to be aware of your basic blocks on this, otherwise you will happily crash your code, which I have done quite frequently. I'll show some examples of this shortly. But it comes with your basic set of dupes, drops, and so on and so forth, which is nice, because a lot of those actually get optimized away. And then you can create words actually in memory. There's several different comma operators here, very similar to the fetch and store primitives. And you'll notice here that they automatically align. There's no fear. I can comma in 3 characters and then do a 64-bit D comma and not have to worry about memory alignment. It has some basic support for strings, which is convenient because that allows me to define text for outputting. And that's basically it. All right. So once you have this representation in memory, what you need to do next is find whether or not you have any kind of constants, and if they're big enough, actually stuff them into memory elsewhere. But to do that, you have to know where your global pointer is located. And that's what this code does. I'm not going to go through the entire thing, but to just give you an example of how small some of these passes are, this is only 61 lines of code. This is how small that particular pass is. But basically, this goes through and identifies whether or not you need to have the global pointer loaded, and if so, it'll interject a pseudo instruction for that purpose. So basically, what I'm doing is the input language defines a set of opcodes that you lay down in memory, but it's not the entire story. There's also a set of opcodes that are specifically related to these compiler passes that you don't get a chance to manually input. And that's kind of the secret as to how this works. And this will actually move instructions. So, for example, if we look at the vacate line here, so I actually vacate a cell right in the compile buffer itself. So after I'm done compiling it, I then step through it again. If I need to vacate a cell, open it up and adjust your pointers as appropriate.
And it actually shrinks down, I mean, like this from your point of view. You have a cell here, it then moves the rest of the guys down.
It's opening up, so it's actually growing by itself. But if I were to do, I do not do any contraction in here, but if I were to do contraction for like a people optimizer, for example, this would be a great laboratory, to explore people optimization. If I were to do that, then yes, I would collapse using exactly that.
This is just saying you're opening it because you're going to add stuff to it.
Correct.
Okay.
Yep.
What is the global pointer at?
So in RISC processors, you don't have the ability to load a 32-bit or 64-bit constant.
Okay.
I'm not aware of any RISC processor that lets you do that. In the case of like a PowerPC, the largest constant that you can load is a 16-bit constant. Now, there's multiple instruction sequences that you can do to synthesize a full word load.
PC relative.
Not even PC relative. Basically, what you do is you can say add high. So you basically say add high, or load high in the case of PowerPC, and what it'll do is it'll take that 16-bit immediate, shift it 16 bits, and then zero out the bottom bits, and then you or immediate the lower bits. So in 2 instructions, you load a 32-bit instruction, or the 32-bit constant. Clever hack, but it breaks down when you get to 64 bits. Because now it's like, oh, now I'm just going to use, 4 instructions, 8 instructions, right? So it gets kind of iffy.
Yeah.
So what people do, and this isn't the only use for a global pointer, but if you study like the Unix ELF ABI specification, not just for x86, but also for ARM, for example, a lot of them will dedicate one register out of their entire set for pointing to a table called a global object table, or GOT.
Oh, yeah, GOT.
And there's also like a PLT as well, but that's also the reference relative to that register. But the idea is that register points to your globals. And if you need a global value that doesn't fit in one instruction or 2 instructions, and you need to load it fast, you stuff that constant into memory relative to that register, and then you load it relative to that register. Right. So this basically what I'm doing here. So instead of having a single global table, though, every colon definition that I make has its own little chunk of globals. So instead of like a 4K block that has globals for the entire, or pointers to globals to the entire program, like what C would do, a single colon definition very often doesn't have any globals. So it's like, why even bother loading
So
or
you're now just relative like link addresses or?
so the RISC-V has, I don't know if I have any assembly examples, but basically the output of the assembler will, actually, hang on. There is actually one spot. It's actually, I just scrolled past it in here now that I think about it. There you go. So there's this instruction here called AUIPC, add upper intermediate relative to program counter. So what this does is it says add this number to the program counter of that instruction and then load it into, store it into this register. So by the time this add immediate DSP -8 runs, GP will point to this instruction directly. So then what I do is I take the address for this particular thing. I'm taking an address relative to GP, and then I'm storing that onto the data set. So this whole .thump definition, that is used, well, as you can see from the comment, that's used for words that you would typically see with create. So this is how I create buffers or arrays or something like that. So that when I execute that word, it executes this chunk of code, which does require loading the global pointer, because otherwise I won't know where in memory it is. And so that's how I derive the address for that. In a typical colon definition, I have to figure out whether or not I need that instruction.
So it's more like high level code than the typical.
Yeah.
Yeah.
Yes, because in high level code, like there's no machine force primitive for load global pointer, right? So I have to interject that into the stream at a slightly lower level, and then.
So you're keeping like a table of link addresses in a way, or as you're pointing to a global pointer now?
No, basically any accumulated constants that I have in the code get tacked onto, I forget if it's the beginning or the end, but it's like immediately at the beginning or immediately at the end of the colon definition. So
Any constants said?
yeah, so take for example the number 2048.
Yeah.
That will overflow the immediate. So if I say add immediate, x16, the value 0,
Yeah.
and then whatever number here, if I put 2048 in here, that will overflow and it will become negative
You
2048.
just compile them at the end of or the beginning of the word of the colon definition.
What's that?
Those just get compiled at the beginning or end of the colon definition.
If they're big enough if they're too big to fit in an instruction like that, yes.
So it's kind of like the pool directive, something similar.
Yeah.
Yeah.
Yeah, and the GP register, the global pool register, that points to that block of memory that holds those constants.
I like that.
This is way better than what C uses, by the way.
Yeah.
The C definition on Linux or even for Windows, like on ARM or stuff, what they do is you have to load your GP register with a pointer to your global object table. And if your stuff still doesn't fit within the global object table, you have to dereference a pointer relative to that. So it ends up becoming a double indirection to get to your relevant global data, if you have. So that's a motivating factor to minimize the number of global variables you have. But for fourth code, have as many globals as you want, because unless you put 4,096 numbers into a colon definition, you're not going to.
Very big.
Yeah, you're not going to run. And in fact, you'll break the compiler before you even get that far. Let's see here.
Trying to remember everything from this because it's not recorded this time, so that's why I'm asking a bunch of questions.
Yeah, no, that's fine.
Can't rewatch it later.
Well, I am actually recording this.
Oh, you are recording?
Yes, everything you see here is going to be on the video.
Good.
Yep. In fact, here's a brilliant example. How big is that number?
That's enormous.
That's
You can feel dyslexic to try to kind of,
yeah. So this from here to there is a 60-bit number. So that address is huge, and deliberately so. Like I wanted to test that functionality. So when I made my emulator, I was like, you know what? I'll be just like the old 8-bit computers of the day, where address 0 is RAM, and then address D000 would be I/O, and then from E000 on it would be ROM and stuff. So I put my I/O like way up in high memory. The problem is you can't just load that value into a register. Like you have to go through these gyrations. And in fact, this is a brilliant example of what I was talking about with the 3 stacks. Because if I wanted to emit a character, I know I've got a character on the data stack, but I can't use it directly because it's not loaded into a register. So I have to execute d-from. So in terms of thought process, I'm moving that parameter from the data stack to the evaluation stack. So now it's in a position where I can actually evaluate with that. D# is basically just like open firmware, basically, except instead of forcing a decimal number, I can actually put hexadecimal here as well. So this just loads a numeric constant onto the stack. So now I've got the character in one register. I've got this value in another register, and then I simply store the stuff. So by the time I execute semicolon, all my registers are dead. They've all been consumed, and I don't have to worry about pushing. I don't have to worry about popping. I don't have to worry about stack manipulation. I never call a subroutine in this, which means that I don't have to worry about saving my stack pointer, my global pointer. I don't have to worry about any of that stuff. It's just maybe 4 instructions. We'll see. There was an assembly output, I think, in this. Here's another example. But here's an example where I don't use such large numbers. Right? So I'm taking 2 values off the data stack. I'm adding 1 to one value, which would be the address. But I'm pushing it back onto the data stack, so now I only have the length to work with. I subtract 1 from the length, and I push that back on the data stack. So in a sense, this is kind of easier because I don't have to deal with swap. Because in fourth, I would have to say swap 1 plus, swap 1 negative. Right? So you don't have that particular mental gyration. It's a different mental gyration. But nonetheless.
It looks cleaner because you don't have because the parameter passing is implicit, but not just, you can make it explicit if you want to.
Correct.
Yeah.
And using, I could pass, 18 different things. In fact, I love how serendipitous this is. Honestly, this is not practice. 0 defetch. That loads a value off the data stack without popping it. So this is like pick, but instead of picking it onto the data stack, you're picking it onto the eval stack. So by the time this while executes, I still have address and length on the data stack. They're still there for me to work with. 1 defetch, that fetches the address, right? So this is how I implement type. So basically I'm saying, while the length is non-zero, grab the address, give me a character from that address. But now I have to push that character onto the data stack because I have to call emit. Yes?
I'm just following the logic here.
Okay.
No, but you have a question here. Sam?
Yes.
Right here.
What's up?
If you have words to explicitly manage the data stack, then what are your literals doing?
The literals are pushing onto the eval stack unless you tell it otherwise.
Okay.
And then here I'm calling next ch. immediately after that. So by the time emit comes back, I invoke next CH directly. So here's a question. What happened to the value in the registers when I call emit?
They disappear.
Exactly. Anytime you have a basic block boundary crossing, your evaluation stack resets to empty. You could have 16 items on the stack. As soon as I execute begin, it's empty, gone. I never have to drop them. Likewise with while, never have to drop them. Likewise after repeat. I do have to drop here. It's kind of optional actually. This might be old code, but I have these two drops here. These are optional because I could just defetch, defetch, and then exit. I wouldn't have to worry about them, but I do make it explicit that I'm dropping it here. Now, because I am calling subroutines, the definition of type does have to have a prologue and does have to have epilogue code. Things that saves the return address, for example. Because when you call a subroutine in a RISC processor, there is no hardware stack. You have to manually save it. And the rest of this is fairly mechanical once you go through those. So let's see. Do I actually have, I don't actually have this stuff. Let's see if I can get this to work. So this is actually building a whole lot more than just that particular code, but I figured this would be a lot simpler than trying to figure out how to do it on a case-by-case basis. So this is actually building, yeah, this is building the emulator. It's building a binary to Verilog program, machine language monitor. There's my assembler. Narrow is a fourth-like language. And there's the SVFIG. So yeah, the sdtest.rom and stuff, that's all related to the operating system that I had written. So now, if I go to source, BSPL, Let's see here, G4th. Somehow I have it here. Well, I'll just do this. So this is what I was talking about. Well, when I was talking about the so basically I have to make room on the return stack. I have to save the return address on the stack, and then I have to load the global pointer, because when I actually make reference to it, that's the value that I'm actually loading at this point here. And so this is the type of code that I'm talking about. Now you'll notice this is actually fairly compact code. This is the type of code that you would expect to see. It's not perfectly equivalent to a human, but it's close enough. Definitely much faster, definitely much more compact than a mechanical macro expansion approach that your typical machine fork compilers use. The equivalent code for that would be stuff like this. I think this is immediately recognizable to almost anyone who programs in Form. So that's what BSPL looks like. It has been used. I consider it my toy language in the sense that I've only used it a couple times, but it has been used to write an operating system. In this particular case, I'm actually writing a device driver for SPI. This is actual SPI code that I use to learn about the protocol. But there are some things that I would like to change going forward. For one thing, I'd really like to get rid of that. If I could get rid of the separate evaluation stack, that would make the program code a lot cleaner. Yeah, because like if you look at stuff like this, like zero defetch, you know, the need to explicitly push data up on the stack somewhere. It would be nice to wrap this into a form that will collapse down to a single instruction, because right now it doesn't do that. But like the need to push D and pop from D and stuff, like all these things. I mean, this particular code is not so bad, but when I was porting STS, it got pretty confusing at a couple times, because there were times when I was transferring, like for example, to execute 2R, for example, from data to return stack, it's two primitives instead of one. So it's kind of annoying, but it does pretty good as a general rule. So how am I going to be using this for the Capsule 3? Well, I'm almost certainly going to be improving the compiler. First and foremost, like you were mentioning before, I'm going to have contractive steps, things like this.
Yes.
That's going away.
Yeah.
So a little bit of peephole optimization is going to be important. The other thing that I'm going to be doing is instead of treating registers X16 through X31 as an evaluation stack, I'm going to try to make it comply more with the C ABI, which involves using a different set of registers, not necessarily contiguously. So that's going to be important, primarily because the chunk of software that I'm going to be using this to write will eventually be running programs written in C. And it would be nice to be able to interoperate without having any thunk layers or anything like that. And as I said, I want to look at ways of getting rid of these defetches and destores and defroms and 2Ds and stuff like
make
that.
it implicit, or
I've got some ideas on how it would be more implicit. I don't guarantee that I'll be able to execute on them, but it's definitely high on my priority list, because I can't tell you how many times I've crashed code because I accidentally forgot a defect.
like make it implicit by default or something?
Right.
Yeah.
Yeah. Or just add more micro passes, if you will, that basically infers stack usage instead of me trying to make it explicit. And as you can see, the typical length of a micropass was less than 100 lines of code. It's not a lot of code. It's just, you just got to sit down and write it. And I didn't bother to do that in this particular case. But I think I can clean up this language pretty significantly. And it's, the bulk of it is there. It's just a matter of shaving off the rough edges, I think. So that's the SPL. It's my fourth language that compiles to surprisingly good. I won't say efficient or terribly good, but surprisingly good RISC-V code. And hopefully with the Kestrel 3 coming up, it will get better.
Cool.
Cool.
Yes. Indeed.
And that's my presentation.